All right, some friction problems. We shall do some static and kinetic linked together. Let's say we have a surface, and on the surface we have a block. And for illustrative purposes, let's say, make something up kind of so we can work this out. The coefficient of static friction is 0.6. Let's say the coefficient of kinetic is 0.37. And we'll say the block has a mass of 10 kilograms. So what's going to happen? Well, we think that's what's going to happen, preferably. And we break this apart into parts. We got to see, oh, and then I have an applied force. That, I forgot to write down. Applied force to the right will be 70 newtons. Okay? So pulling this way with the force of 70 newtons. So, I won't draw all the free body diagram stuff, but maybe that. We know we got gravity pulling down, obviously, the floor pushing up, got the normal force, gravitational force, we're going to have friction, applied force. So if the applied force is here, then we need to see if the block's going to move in the first place. So static works up to a certain point. It's like we said, like a spring. If you pull a little bit, it exerts a little bit of force to match it. If you pull more, it exerts more force. You can think of it that way. So static friction exerts enough force until you break the spring. Like maybe some of them cheap plastic springs, you can pull a little bit, then you can break. So friction works up into a point and only matches what you do. If you start pulling more, it pulls more back, and then you release, and it releases back. You pull more, and then you start going back, and it's doing less. It's matching. So it zeroes out, so the block stays there, and that's how we know. Thankfully, Newton came up with the idea that forces come in pairs. Otherwise, we couldn't do a lot of stuff. Just like in quadratic equations, if we, nobody cares about multiplying to make 0 in elementary school, but that is an important thing for a lot of stuff. Multiplying to make 0 is critical in solving a lot of stuff in a higher level. Same thing, the third law might seem like, who cares? But if it weren't for the third law with balanced forces, Newton was the one that identified that when there's one force, there's going to be equal and opposite, and inertia and stuff. If not for that, we couldn't do some of this. So it's this little thing that seems irrelevant, but actually has important implications, and it's very practical. So friction works up to a point, because of Newton's third law. So, and we can tell because it's not moving. The block's not moving, no change in velocity, no net force. So, and remember, the force of friction is going to be between 0 and this, or the normal force, or as IB likes to call it, R. So F normal or R, like that. Okay, now force of friction will be between 0 and this, 6/10 of the normal force. And the normal force is its weight, because nothing's pulling it up to less than the normal force. So the ground has to support all the weight. So we need to see what the weight is. Remember, kilograms is mass. It's not a weight. Weight is force, newtons. So we get this. We do F equals ma for weight. Weight is mass times acceleration due to gravity. It's an example of that. And then we got the weight is 10 times 9.8. So 98 newtons, about 22 pounds. So the weight down is 98 pounds. And that'd be like the R, F sub n, or R, because that's the weight. And remember, the weight's pulling down, and the normal force is pushing up to zero out. So the weight is the same as the normal force. So by Newton's laws, this implies that R or F sub n is 98. Okay. And then we got to see, we take a fraction of this to see if the applied force can pull it. Friction can go up to this amount. So with this much weight in this coefficient of friction, then the force of friction, if we do 6/10 of 98, I'll approximate and just say it's about 60, because 100 times 0.6 is 60. And 54, 59.6, I don't know, I can say 59.6, I guess, if I did my mental math right. That'd be 8. 54, 58.8, 6. Okay, 6 times 9 is 54. 6 times 8 is 48. 54 and 48 is 588. Okay, so the force of friction is in between there, like a spring that can go up to this amount and then it breaks. And then kinetic friction would take over, kind of like our force, the applied force, is more than what friction can handle. Oh, I was thinking about spring, and I actually didn't put an S, force of friction. Okay. So we're going to be able to pull it. We're going to pull, and it can't resist enough, then we pull it off. So it starts moving. And then, bam, we got kinetic friction. Okay. So we know that the block will move. Friction cannot overcome this force. It's not more. This is less than what we're pulling with the pulling on the block. So that's step one. Okay. So to kind of review, we get the weight. We got the weight to know the normal force because they're equal but opposite. Then we get the normal force, take a fraction of it, and we get this. And so remember, it's like force of friction, we get this. We did static friction times the normal force, static, in other words, like times what they call R and the IB stuffy stuff. Okay, so it's a review. Now, moving on, next step, 1, 2, 3. Now we go kinetic friction. So again, it's going to be a fraction of the normal force, a fraction of the weight. Now, with kinetic, I guess I should have labeled that static. I was so busy talking about it and smelling my chili that's in the oven ready to eat that I didn't think about it. Sorry. Blame it on the chili. Original recipe chili too, from like back when it was first developed. Authentic original chili. Now, the kinetic, we're going to do a fraction of this, fraction of normal. So kinetic friction will be kinetic coefficient times the normal, which, you know, for IB would be with an R. And it's just moving, so it's just that. Then we do our 0.37 times 98, our coefficient times our weight times the normal force, and we're going to get about 37. I don't know if my calculator handy. So you can do 98 times 0.37 and see what you get. I'm just going to put 37 to round off. 37 newtons. So we got 37 newtons of kinetic this way, 70 that way. We get our total. So the net force is 70 minus 37, which is 33. So we're pulling with a net of 33 newtons. 70 decreased by the 37. 37 is always this way. I'll go ahead and draw it in here at this point. So you got 37 newtons this way because of the kinetic friction. Then we can see how it's accelerating because, you know, F equals ma. So what's acceleration? What's a change in velocity? From going from nothing to moving, it would be the net force divided by the mass. So acceleration would be net force over mass, which is 33 over 10, which is 3.3 meters per second squared. And then, isn't this awesome? Now we have an acceleration, and we can do all the fun, awesome equation of motion stuff we've already done. We can see what is change of velocity, what its velocity will be in a certain time. Because its initial velocity is 0. Initial is 0, u is 0 in the IB speak. What's v after a certain time, and all that stuff. But there's some basics on using static and kinetic in a problem. Peace.